is all about double integrals over more general regions. So I guess the question is, what do I mean by this? More general regions. Well, what was section 1? Section 1 was also double integrals, but the difference was, okay, the region on the xy plane underneath the surface, right? In section 1 was what shape? A rectangle. Okay, so we had a rectangle. Today we're going to do things that are not rectangles. Now I remember a week ago when I was giving you guys kind of the preliminary overview, I gave you a picture that looks kind of like this one in your book that I want to direct you to. So let me go ahead and punch this up. General regions of integration. Hey, we talked about Riemann sums a lot last time. I gave you a picture kind of like this one. I don't think it was two-dimensional. I think it was three-dimensional. So anytime you see a picture like this, right, and realize that what you can do is you can increase the number of x divisions or the number of y divisions. I'll really increase the y divisions, make thin rectangles, right? But what we're looking for is we're looking for rectangles that are entirely contained within the region we're talking about, right? And obviously what happens is, just like in the Calc 1 case, you send delta to 0, so the size of your partition. And when you do that, the idea is you fill it up, okay? You get, if you can compute this limit as the size of the partition goes to 0, then, and again, last time you may remember we were, trying to compute volumes. Let me see if I can use this little. Here's the picture, right? So we want the area under the curve. No, we want the volume under the surface, right? That's the analogy here. And so again, this is what you might call an inner sum. An inner sum. Okay. You could also imagine somehow there's an outer sum where you'd kind of get closer and closer, but that's maybe harder to understand, and so we kind of stay away from that. I think this one allows me to do the same thing. Yeah, there we go. I can change number of divisions. I wanted to do this show volume, but it's not letting me do that right now. Okay.
You would have to hit delta goes to 0.
Oh, I didn't want that. Well, okay. If we let delta go to 0, now it'll let me show the volume that I'm computing, right? So this, the volume of this object, whatever it is the integral. Thanks, Matthew. So once again, how do we compute this? It's not by doing limits. It's by doing integration, okay? Antiderivatives. And in particular, it's doing what are called iterated integrals, okay? Now, what's the difference? The difference is your region R may take on all different kinds of shapes. And what we're going to imagine is that two of the sides are really nice in that they can be expressed as functions. Okay? And when you have that situation, then this thing becomes computable, let's say. Okay? Easier to compute. And so I'll have to give you examples where that happens. So let's maybe take this example here. If I said well, it's interesting. This is a good way to do this, maybe. So here's my example. Find the volume of the solid. Let me remove this. This doesn't have to be there. Again, above the xy plane. That's always what we're talking about, right? Bounded by, I'll give you the names of these things. The first one's called an elliptic paraboloid. So that equation would be z equals x squared plus 4y squared. Okay. And the cylinder x squared plus 4y squared equals 4. Let's try to get some kind of an idea of what this looks like. Well, maybe the first thing to comment on is that this equation here, right? If I just think of what it looks like in the xy plane, what shape is this thing? It's an ellipse, right? I mean, if you divide everything by 4, you get x squared over 4 plus y squared over 1 equals 1. And so this is an ellipse that in the x direction comes out 2 in each direction, but in the y direction it comes out 1. And so think of this green ellipse. But why do we call it a cylinder? Because z can be anything you want, right? So take that ellipse and just shift it up the z-axis or shift it down the z-axis, and somehow this cylinder, am I making that something you can imagine? I'll try. Okay. This may be more challenging. X squared plus 4y squared. Well, wait a minute. Okay, so if z equals 4, right, then I have exactly that equation. X squared plus 4y squared equals 4. So if I'm telling you that this ellipse I drew up here is actually at a height z equals 4, somehow that's the intersection of the two surfaces. Does that make sense to you guys? Now, other things happen too, like what if x squared plus 4y squared equals 0? Well, that would be, the only solution that would have would be 0, 0, right? So that would be here at the origin. Or if x squared plus 4y squared equals 1, let me think about that for a second. X squared plus 4y squared equals 1. You know what I'm really doing here is I'm doing level curves, right? So that means you can rewrite that as x squared plus y squared over 1/4 equals 1. So again, it's x over 1, so I come out 1 in each direction. This is at a height of z equals 1. I come out 1 in each direction and only 1/4 in each direction. So you get an ellipse, but it's smaller. And so when they say this is an elliptic paraboloid, I guess what I'm picturing is something that kind of gets opened up. And the intersection between my green cylinder and the pink bowl, if you want, or the orange bowl, is this pink ellipse right here. Does that make sense? Maybe what doesn't make sense is, what am I finding the volume of? Let me see. Find the volume of the solid above the xy plane, bounded by the paraboloid and the cylinder. Well, maybe you can see it. What I'm picturing, maybe I can draw it a little better. I have this paraboloid, which goes like this, right? And it gets wider. And then I have the cylinder I had drawn in green. So the cylinder just kind of goes vertically, right? and then it kind of hits here at the bottom. And so what I'm really finding the volume of kind of surrounds the bowl. Does that make sense to you guys? It surrounds the bowl, you might say. So any questions on this so far? Yeah. It says the volume of the solid above the xy plane. So the xy plane I'm picturing right here. Here's the point 0, 0, 0.
So it's between the plane and the...
Between the plane and the bowl. Yeah, but no farther than the cylinder, right? I guess what's important here is you need to realize that when we talk about your double integral, right? My double integral is going to be represented this way. We're going to integrate over R, okay? What are we going to integrate? Well, we're underneath what surface? This one, right? Z equals x squared plus 4y squared. So we're underneath that. So that's what goes here, x squared plus 4y squared. And do you remember what it is that I draw here, or what I put for my differential? I write d what? dA, okay? And A, again, is one of the areas of these little tiny small rectangles. But I think what's important, more important than either of these sketches, guys, you don't necessarily need to do these sketches when you're doing a problem like this, but what it is important that you do is you need to draw R. You need to draw what R is. I mean, just let me draw it just in the xy plane. So that xy plane that I had, here was x, here was y. I'm gonna just put it here for a second. And I understand now that R is the region in the plane which is kind of the shadow of this, right? So it's the boundary. So again, it went out 2 in each direction, and it went 1 along the y-axis. And so this ellipse, right, this is my region R. Does that make sense to you guys?
So is your region R always the shape of whatever's at the base of the plane?
Yeah, the region R is going to be on the xy plane. It's going to be on the xy plane. It's the region R is where those little tiny rectangles with area A are going to show up inside. So it's important to sketch that region. And then what we're going to do is we're going to, well, one of 2 ways to do this, I guess. I guess either we can integrate, so again, the idea is we compute this as an iterated integral. Okay? So you either compute dx dy or you compute dy dx. I think the first way I'll show you is dy dx. Or integrate dx dy. And by the way, I'm about to do a trick that you guys should try to use as often as possible in this chapter. Okay? I said I wanted to integrate over the region R, right? But maybe a better plan would be, let's just integrate over this region, right? Get my answer and multiply by 4. So that's what I'm going to do. Why is it a good plan? Because the limits of integration end up being nicer. So let's show you how it works dy dx. Let me show you that first. Okay? So when I do it dy dx, here's what I do. Again, you don't need to draw these brackets, but maybe when you're first learning it might be useful. There's going to be an integral inside, and then I'm going to get an integral outside. Okay? And when I split it up dx, there will be numbers on the outmost integral. Because, well, what am I going to integrate? From this x value, x equals 0, to this x value, which is x equals what? 2. So I can tell you right now that when I compute the integral, it's going to go from 0 to 2. That's the dx part. Now for the dy part, things are a little different. The dy part, you want to think of, at any one particular place, right? So there's a rectangle here. Thanks, Duncan. And so the question is, what is the upper bound for y and what is the lower bound for y? And I need you to understand that what's going to go here and here, we are going to put functions of x. Okay? So when we write dy, that goes here and that goes here. Okay? So the upper curve, can we express that as a function of x? Well, remember what that curve was. That curve was x squared plus 4y squared equals 4, right? So I'll solve for y. I'll get 4y squared is 4 minus x squared. And so I'll get that this curve would be y equals, let's see, if I divide by 4, I guess I have, well, okay. It's the square root of 1/4 of 4 minus x squared, right? You guys see that? Or is that too fast? With me? Who's with me? Just so I know I'm not flying. Okay. So that's this curve up here, right? And so the upper limit, what you would see written here, and actually you could simplify that, right? This is, if I take out the square root of 1/4 times the square root of 4 minus x squared, right? That's what y equals. That's that upper curve. And so what I have here is I just have 1/2 the square root of 4 minus x squared. That's the upper limit of the quarter of the region that I'm doing. And now what's the lower limit? The lower limit would be 0. Y equals 0. I mean, it's a function of x, but it's just, right? It's really y equals 0 is this line. And that's where the payoff is, guys. What would happen if you did the whole region? Well, you would go, remember when you were solving for y, there's a step I skipped. Really, when I take the square root, I'm supposed to put what? Plus or minus. So you could go from positive, and then you could go down here, you could put negative, the same thing. But I'm telling you that this is a lot faster. And so you may as well get in the habit now. Okay? Look for symmetry. It's a huge help, particularly in Calc 3. Engineers do this all the time. They want to build a three-dimensional part. They want to talk about its volume. What they do is they center the thing at 0, 0, or strategically place it so that you can use all these symmetries that you have in an object. Okay? And then I guess what we have to do now is we just have to integrate, well, x squared plus 4y squared, first with respect to y and then with respect to x. Okay? You can also do this one dx dy. And it is probably worth our time to think about what that would be. So I will pause, and let you guys see if you could take the same exact region and set up what it would look like if you did it dx dy, okay? What would be the limits of integration? Start with the outside and then do the inside, okay? I'll pause for just a minute or two and let you do that. All right, I gave you a minute. Let me see if I can earn my pay here and do this. The outside limits would be, if you're integrating dy, see, you want to think about kind of moving along, making little rectangles this way, right? Like I did that little black rectangle. And so the outer limits this time are y values. And so we go from y equals 0 to y equals 1 this time, because that's the height of the ellipse. See the difference? Now what about the inside? Well, the functions this time are bounded by x functions. X as a function of y. And I hope you understand that this is going to be 0, right? Because x equals 0 is the left border. But when I look at this black rectangle, again, it's hitting the ellipse on the right. Yeah, Ryan?
The second equation you have listed right next to that circle in red, is that supposed to be 4 minus x squared?
Where?
Your second, like right next, yeah, right there.
That's a 4 minus x squared, yeah. So's that. And so's that. Too small.
It looks like it's just 4x squared. Right.
You're right. And I'm going to remedy that now. I'm going to make it really nice when I do this limit. I'm sorry about that. This right here, right? This is the one I want you guys to compute. What's that limit? So let me be more clear. Let me be larger as I do this. X squared plus 4y squared equals 4. Right? Because there's a minus there, and Ryan couldn't see it. I'm sorry about that. So let's make it bigger and more clear. So what am I solving for this time, though?
X.
Now I'm solving for x. We're writing x as a function of y. You guys did that before, right? I remember in Calc 2, there were times that, remember the old finding the area between two curves? There were times that you had to write x as a function of y to get the integral to work out. Same thing's going to be true here sometimes. This problem can be done either way. That's kind of a nice example to start with. All right, so what do we get? We get x squared equals 4 minus 4y squared. I'm going to make this nice and clear. And so when I take the square root, I know normally what I need is I need a plus or minus the square root of 4 minus 4y squared. But clearly this border is going to be which one, plus or minus? The plus. So we will put, right here, we would put square root of 4 minus 4y squared. I'll try and make that minus big enough. And then again, what are we integrating? Excuse me, x equals 0, you got in the way. We're integrating, again, x squared plus 4y squared. Are you with me? Okay. I feel like I should probably do one of these. Do the integration as an example. So I will. Do you want to see the one on the left or the one on the right? Because I don't care.
To the left.
The left. Well, we have space for it, right? All right, so let's do the one on the left. So here I go. When I integrate this thing with respect to y, so here, let me write out as clearly as I can. I have the 4, I want to remember that. I have the integral from 0 to 2, and again, that's dx. What I'm working on right now is just this part in here. So let me pick a color. How about blue? There we go. So when I integrate that function with respect to y, what do I get? Well, x squared, you treat that as a constant, so it's just x squared times y, right? If you had a 4, it would become 4y. If you had a 7, it would become 7y. But here, this piece has y's in it. So do you know what I'm going to write here? Plus, good, 4/3 y cubed. And then I'm going to draw my line. And, you know, I don't think the book necessarily does this, but I like to do it. I like to write down y equals, to remind myself, okay, what am I substituting in where? Y equals 0, and up here this is y equals 1/2 square root of 4 minus x squared. Okay, so that is going to be substituted in for y in each case. So here I go. The next step, this equals 4 times the integral from 0 to 2 of what? Well, I guess, first of all, notice, when I plug in y equals 0 to either one of these, they go away. Huge advantage for that symmetry again. Otherwise, this expression would be very long because you'd have to do f of b minus f of a. Okay, so again, I'm demonstrating that. So I guess the only thing I really need to plug in is this. So I have 1/2, I'm going to write the x squared and then I'll write the square root. X squared square root of 4 minus x squared. Wow, okay. Plus 4/3. Okay. And now what do I have here? Well, when I cube 1/2, that's times 1/8, right? And when I cube the square root, I get 4 minus x squared to the what? To the 3/2 power. Yeah. Yeah. Nice. Dx. Yeah? So all you have to do is integrate that now. And you're done. And this is a Calc 1 problem, so I don't have to do it.
Can you scroll for a second?
Sure. What do you want to see, Ryan?
Just one of the other things.
Can you see it?
Yeah.
Maybe I'm going to pause and put that in my calculator. That'd be kind of cool. But let's say a couple things about this integral. If you were going to integrate it, what techniques could you use? Substitution, I agree. What kind of substitution?
Trig substitution. Yeah, you're going to do it.
You're never going to get that. Yeah.
There's an inverse trig sub that comes in handy. Yeah. Do you know what the sub is?
1 minus x squared.
The sub ends up being theta equals the inverse sine. You might remember that if you have a squared minus u squared, that's an inverse sine. When do you use inverse tangent? Do you remember that one? If it has a plus, you use inverse tangent. Yeah, if it's a squared plus. Anyways, the correct substitution, I believe, would be let theta be the inverse sine of x over 2 here. Okay? And use your Calc 2 skills. And we get, according to what I have here, we get 4 pi. Isn't that beautiful? Nice job. Nice job, guys.
Comes out that the yeah.
Well, because, yeah, you're plugging in a 2, you're plugging in a 0. The 2 over 2, the inverse sine of 1, that's a nice angle. But then you end up getting, I mean, we can show it, but I don't want to do it now.
But you
Okay?
might work it out and upload it for us to go out
Is that what you want?
for.
Okay. If I have nothing else to do in office hours, that's what I'm doing. That'd be fun. All right. A couple things to say about it. This is a warning that you will have to remember some of your Calc 2 for Calc 3. Surprise, surprise. Right? So you're going to encounter that in the homework for this section. Okay. Secondly is, sometimes there are better ways to do this. Okay? Matter of fact, this is great. I'm just going to show you this, and then I'm going to not do it, because again, I respect your time. I guess I didn't used to respect their time. Here, find the volume V bounded above by 4 minus x squared minus y squared. Do you know what shape that would be? Z equals 4 minus x squared minus y squared. A downward paraboloid, sure. I guess one of the differences is the one we did, we called an elliptic paraboloid, right? Because it was ellipses. This one, take the thing, but because the x squared and y squared have the same coefficients, it's a circle, right? And so I start to work it out, and I'm working out, and I'm using inverse sine, kind of like I recommended there. I got a cosine to the 4th power. I said, ouch. I end up getting 8 pi for that one. But it works, okay? But I loved what I wrote here. These are from 2007. This is my first year at Lakeland. No, my last year at Case, because this is spring. Ugly example to kill the class and motivate the use of polar coordinates. You see, for a problem like that, you can do it with enough trig subs, and it can be done. Or you could do what I said. You could use a calculator. And that's actually good to know because, you know, can my calculator do a double integral? Not really, but maybe if I can reduce it to a Calc 1 problem, then maybe I know what to do, right? So what I feel like the skill is we're developing here for you guys is not so much the Calc 2 anymore, although, trust me, you're going to remember this as you work. But it's setting it up. And again, I think the most important part of what we're learning today is how to sketch the region and how to write the limits of integration. And maybe when to do what. That's some of what's going on also. Okay? Yeah, but section 3 of this chapter, chapter 15, is all about polar coordinates. And actually, you can imagine that again, I keep talking about symmetry. Well, there's so much symmetry in the world of engineering. There's so many circles that come into play that it seems almost natural to use polar coordinates for the XY plane in many applications. This ellipse is not really one of those. Okay? But many times you get circles or things where polar coordinates are going to help, and that's coming after spring break on Monday, first day we get back. Okay? So, questions so far on the first example? If we go back to the book. Yeah, I liked this one. So, again, you could show the surface or not, right? The surface is getting higher and higher, right? If you think about this, here's a function h of x and here's a function g of x. And so what we're doing when we pick a particular x value, remember how I drew the rectangle on the region? See, what you need is you need to have two nice functions, like if they're continuous, let's say. That's a good region then. I would call this region vertically simple, is what I would say. Okay? So maybe I'll give you a definition or two for that. So sometimes my region R is vertically simple. What do I mean by that? I mean, i.e., bounded above and below by continuous functions of x. And that was the picture we just showed you here, right? You have h of x is in black. and g of x was in red. I'll draw it in pink. So here's y equals g of x, and here's y equals h of x. And so again, I guess the question is, in this situation, if this is my region R, right, am I going to integrate, so in this case, we integrate how? Do you guys think I'm going to want to do dy dx or dx dy? What I like to tell people is, well, think about what the last thing you're going to do is you want to go from a number to a number. What you want to do initially is go, on the inside, is go from a function to a function, right? And so basically, the inner integral here, right, we're going to put y equals g of x as the lower value and y equals h of x as the upper value. And so the inside integral is going to be dy. And the outer integral then is going to be what? Dx. And what would that be? I guess I'll call this x equals a, and I'll call this x equals b. These lines, right? Sometimes they're not lines. Sometimes you might have, maybe these things intersect at a point. But you'll still, the last integral you do, you have to have numbers here, a and b. You have to put functions on the inside. And they have to be, I said continuous. They don't have to be continuous, but they have to be nice. Continuous definitely helps. Okay, because if it's continuous, it's integrable. Oh, and then what's the only thing that's missing is the integrand. The integrand would be f of x comma y, right? It's some function z, which is a surface. Okay. What's the other possibility? If my region R is what? Horizontally simple. I don't want to define it, but you can imagine what that means. Then we can set it up this way. We're going to set it up dx on the inside and dy on the outside, right? And so this will be x is g of y and x is h of y, right? And then the outer numbers, again, I'll just put c and d because they're numbers. And again, this is my f of xy. So it really comes down to sketching the region, and that tells you what to do. Is this okay? And there's a few other ideas, I think, mentioned on the... So again, if I hit play here, this is kind of cool. You could see the function moving.
Do you have time to look at quick check through?
Sure. Let's go there now.
It's right, they're all the way at the end.
Notice it says we're going to talk about choosing and changing the order of integration. Now, I guess what I was just talking about is choosing. You're looking for vertically simple or horizontally simple. But there are other things that might influence your choice. I mean, you guys made a choice on the first example, right? We decided to integrate it this way. Would there be an advantage to integrating it that way? I don't know. I guess you wouldn't end up with the 1/2. Sometimes there's a very large advantage. Sometimes there's a problem where you can't integrate it one way from a calculus 1 standpoint, but you can integrate it if you try the other order of integration. So that's some of what this section's talking about. Let me get to that at quick check 3. What do you think, guys? Vertically simple or horizontally simple? Or both? Right?
Oh, I didn't see the blue.
This is a nice
I
one.
didn't see the blue there.
Yeah, this one's both, right?
Yeah.
You can see as R goes by, yeah, I mean, we're always kind of nice and continuous, all right. Volume of a tetrahedron was a nice example. Here's quick check 3. Change the order of integration of the integral 0 to 1, 0 to y, f of xy dx dy. Again, what did I say is the most important part of everything we're doing in this section? It's drawing the region R. Let's see if we can do that for this problem, okay? So we have quick check 3. I think the first thing I'm going to do is I'm just going to write down that integral, and then I'll try to draw the region R. Because they don't even tell me what the function is. They don't care. They just want to see, can you, by drawing the region R, make sense of what's going on, right? So the idea is, eventually, what we'd like to do is we'd like to say that this equals some integral where it's f of xy still, but it's going to be dy dx, right? So let's draw the region. Well, let's first of all draw the xy plane. Then I'll think about drawing the region. And I think I've told you guys I like to work outside in. I really think that's helpful because I know on the outside I'm going to be drawing lines. What kind of lines should I draw? Vertical lines or horizontal lines in this case? Maybe even easier. What are the equations of the two lines that I should be plotting on my plane here? The key is we're working outside in, right? dy has to do with that integral, right? So we're talking about this line, which is y equals 0, right? To this line, which is what? Y equals 1. And that means that what I'm talking about here, okay, again, x as a function of y. So the other part of this, what we're doing is we're thinking, as I look at this piece of it, right, I'm thinking about x equals 0 to x equals y. Do you guys know what x equals 0 looks like? I hope so. Sure, that's this y-axis, right? X equals 0 is this line here. Do we know what x equals y looks like? Yeah, but I don't usually call it that. I usually call it the line what? Y equals x, right? So here is the other line. And so if you ask me, Paul, where is the region? I would tell you it's right in here. Do you guys see that triangle? That's the region. Who's with me so far? Okay, so now let's rewrite this as a same integral, a double integral, but we want to write it dy dx. Okay, so the outer thing I need are the x's. I need numbers, right? What are the numbers that go with x direction? Well, I guess they go from here, x equals 0, to x equals what? How do you know? I guess what you need to do is you bet. Yeah. Now, this was a particular easy problem. Sometimes they're going to tell you, hey, bounded by this curve and bounded by that curve, and you won't know where they intersect, but you can do algebra, college algebra that I shouldn't do in a Calc 3 class, and you can solve it, right? And so somehow we figured out that that's 1, 1. Nice job, guys. And so that means that the other line would be x equals 1. So when I integrate dx, I'm going to be going from 0 to 1. But what I like to do then is draw a particularly small rectangle of size delta x in here, right? and I'm, or maybe dx, right? If it's really infinitely small. But as I look at that, I ask, what is the lower bound and what is the upper bound? And they should be functions, right? And they're not going to be functions of y. They're going to be like this, g of x and h of x. So what is g of x? What's the lower bound of this region R? Isn't it just this line here, g of x equals x, right? That's the lower bound, x. And the upper bound would be g of x equals 1. And that goes here. Because that's this here. I think it's a great quick check. I think this is the skill that's new. The other stuff, not so bad. So I'm glad they're having you practice this. Okay. All right. I'm going to give you guys a break because we're past 10:50. Take our 10 minutes, and we'll come back to... I definitely want to do example 5 today, and we'll see what else we do. Let's start. So, yeah, not much to say here except that this, like they said, this is an extension of the area between two curves. You can find the volume between two surfaces. That equation up there at the top probably makes sense to you, right? G minus F. I used to tell people in Calc 2, it's top minus bottom, right? The top function, and sometimes that would switch, and when that happened, you divide it up into two integrals. We'll have that kind of situation also, okay, where the top and the bottom can switch. If you were integrating dy, I used to say right minus left. Okay, so anyways, oh, here's example 5. I thought so. Okay, so find the volume of the solid bounded by the paraboloids z equals x squared plus y squared and z equals 8 minus x squared minus y squared. So I don't know how much of this to do because a lot of it's in your book, but I think some of it would be worthwhile. So let's try it. Nice thing is I don't have to draw as many pictures, right? I have z equals, so this is some notes about example 5 from the book. So I have z equals what? X squared plus y squared. Oh, so what shape is that? X squared plus y squared equals, well, if it said r squared, that's a circle, right? At wherever z is, right? So we have a bunch of circles for level curves. But as z gets bigger, right? I mean, if you just fix one, you see a parabola. So this is your paraboloid again. And then they have another paraboloid. They have z equals 8 minus x squared minus y squared. By the way, I wonder... What's that?
That's shifted up 8 and then opening.
But opening downward, yeah. So you can see them here. They have these nice sketches. Let me make it just a little bit bigger. Okay, so here's z minus 8 minus x squared minus y squared, opening downward like that. And here's the other one, right? So what do we want to do first? I guess we want to figure out where this intersection is. And then what we're finding, guys, is that the volume of this bean in here, or whatever it is. With me? Actually, it looks like those plastic Easter eggs, right? Maybe this is how they make them. Well, I doubt it. But anyways, we're here, right? So again, we're going to do top minus bottom is the plan. Okay? Which one's the top and which one's the bottom? Well, I guess this is the top, right? And this is the bottom. And so I guess what I'm going to do to find the volume... Oh, does this work out nice? We're going to do a double integral over some region R. I'll just write dA. And when I do top minus bottom, right, I get 8 minus x squared minus y squared. And then I have to subtract x squared plus y squared. So that's not too bad, right? What we're going to be integrating here is 8 minus 2x squared minus 2y squared. Now, I guess the next question is, do I want to do dx dy? Do I want to do dy dx? Another question would be, do I want to use symmetry? And the answer is, yes, please, use symmetry. So what we want to do now, I think, is we want to sketch R, right? So, yeah, R is going to be the region kind of underneath the surfaces, right? The shadow is a nice way to say it, yeah. And in particular, I guess what I really need, because these are oriented the way they are, vertically, right? We have Z and we have Z. This is really nice. So what I really need is I need to know, where do these two curves intersect, right? So again, maybe I'll do that up here. Find the intersection. Because then the intersection we can project down, and that's going to give me the boundary of R. And again, we have Z equals this and we have Z equals that. So I guess what I have is I have x squared plus y squared is equal to 8 minus x squared minus y squared. That's the intersection, right? So 2 times the quantity x squared plus y squared is equal to 8, or x squared plus y squared equals 4. Ah, okay. So this is a circle of radius 2. That's a better picture of my region. It's a circle of radius 2. Actually, you could see it on the, if you just show the intersection, right? That's this. And let me not show the surface anymore. Let me just show that region. So what I'll do is I'll project that intersection down, and that's the region. Okay, see that? And now it says restrict to the first quadrant. How come? What's the strategy that they're implementing here?
Symmetry.
Yeah, symmetry, right? So really what I want to do is I want to say that the volume is equal to, let's see if we could set it up now, right? So it would be 4, and then do we want to do dy dx or dx dy? I guess it doesn't matter too much, right? I think if it were me, I would just solve for y. I mean, there's all kinds of symmetry, but y here is going to be, if I just restrict myself to here, it's the square root of 4 minus x squared, right? So looking at this piece in here and looking at a vertical rectangle here, I could say we will integrate dy and we will integrate dx. What are the x boundaries? As I'm looking at this stuff in here, 0 to 2, yeah, so 0 to 2. And the y boundaries, this is the function y equals 0, and the upper function is that y equals square root of 4 minus x squared. And I think that's all I want to do. I'm hoping the book does the other calculations for us, but that's what I want to do. Let's take a peek, see what they do. Make it smaller in case you're still looking at the stuff I was writing. Ah, get out of here, section 1. Okay, solution to this. Dun, da, da, da. Yeah. Important thing is, did we set this up right? Interesting. Something a little different about what they did. They have an 8. What else is different? Well, you see, they have 4 minus x squared minus y squared, right? So they basically took one of the 2's out, which makes sense. Right? Why not? Why not? They evaluate the integral. How do they do this? I love this. One line. Trig substitution. Think about how long. And then another one line. evaluate it. Right? Didn't that take like a page and a half in Calc 2? I don't know. Although there are tricks to evaluating the cosine fourth power when you happen to have 0 and pi over 2. Something, if you're interested, Wallace's formula could be used, and they did not do that. But that's something you could look up. Did you do that? Yeah. Wallace's formula is let me show that here. It could be used for example 5. I think so, anyways. All right, enough of that. That's good. The next point that the book tries to make is here. Decomposition of regions. Sometimes, and this happened in Calc 2, you get a region like there, that's the whole picture. You get a region like this. What's the problem with my region? It's not vertically simple, and it's not horizontally simple. But sometimes you can divide it into regions where then you can handle these things separately. And that needs to be done at times. Would it be vertically simple or horizontally simple there? Well, maybe. I think there's better things we can do. But a good example of this I have here, and I thought I'd work through it now. Okay. Oh, and actually, one of the good things about this example, too, is that it also demonstrates the last point. Look. Finding area by double integrals. Now, wait a minute. Double integrals represent, you told me what? Volume under a surface. So how could you use a double integral to find area, and why would you? And the answer is sometimes that's an easier way to approach it than what you did in Calc 1 or Calc 2. Here, see if this picture helps make sense of the whole thing. Ta-da! What is that? That's the surface z equals 1, right? And if you think about z equaling 1, the volume of this surface is exactly the same as the area of the region, right? So you can think of, if I have to find the area of the region, I'm just going to integrate 1 with a double integral. Here's your formula. Right? So let's do it. Let's do it. So here's a problem that I'd like to work out together. Find the area of the region bounded by, and I'm going to give you a few equations here. So let's look at, well, y equals x, y equals 2x, and x times y equals 2. The first two equations are lines. Do you guys know what the third equation is? Yeah, what is that called?
It was a rational function.
It is a rational function.
It has asymptotes at
Oh, okay.
Right, I mean, I guess we could write it as y equals 2 over x.
But then that's going to be like shifted up and down.
It's called a hyperbola, actually. It's a hyperbola. It's just that, you know, when we study the conic sections, the ones we usually skip are the ones that are rotated. And yet, I like to say that y equals 1 over x is one of the most important functions in calculus, right? So I guess, how do I plot this? Well, like you guys told me, the axes are actually asymptotes. Do we have any points that this thing goes through? Well, we will shortly. Let's graph y equals x, right? So y equals x I'll graph in green. I'd like to know what that point of intersection is eventually. So here's y equals x. And I'm also going to graph y equals 2x. Maybe I'll do that in brown. And so that's more like this, right? It's a little steeper. I guess I'd like to know that point. Tell you what, I'll find this point of intersection. You guys find those. This one's 0, 0. So how do you find your points of intersection? Yes, that's one of them. Radical 2 would be this one. Right? You could substitute, right? Let's find that last one. Let's actually work it out. I mean, if y equals to 2x, then I know that I have 2x is equal to 2 over x. And so I get x squared is equal to 1. Oh, so x is plus or minus 1. Actually, that's interesting. Does that mean this also intersects at negative 1? Well, the answer is yes, because if you plotted the whole thing of xy equals 2, that'd be down here. Okay, so I don't want to be confusing, so I'm going to say find the area in quadrant 1. Sorry about that. Of the region bounded by these curves. And so, do you guys see what region I'm talking about? I'm talking about this region in blue in here. That's what I'm trying to find the area of. What point is that? I guess it would be, that's point 1 comma 2? Right? Yeah, if I plug a 2 in for x, y equals 1 in either of these two equations. So what it's time to do is use our zoom feature of our magic marker. So we can zoom in. It's really nice. Let's do that. So we have, the region looks like this. There's a line, and there's another line not quite as steep, and there's a curve. And this is the region R I'm interested in. And we have the coordinates of these 3 points, so I'm going to write those down again. This is the square root of 2, square root of 2, and this is 1 comma 2, and this is 0 comma 0. And now the question is, how do I do this? How do I write this or compute this area? I guess you have to decide, do you want to do it dx dy or do you want to do it dy dx, right? Oh, since I'm finding the area, at least I know what I'm going to be doing the double integral of. The area, we know, is the double integral of my region R, where I just integrate 1. That's what I have to double integrate, right? So what does this equal? Well, I claim what we're going to do is we're going to split it up into pieces. 2 double integrals. Where? Where do I need to switch? Like, if I'm going, let's say I'm going to do dy dx. So we're going to integrate 1 dy dx, okay? You see, what I'm saying is, you're going to want to make a switch, because we're going to go x equals 0 to 1. That's right here. But then we want to change for this part. Why? Because the upper function, the top function, right, has changed at that point. Do you see that? That's the kind of thing you want to look for on these regions that are more complex. So I guess from 0 to 1, what would I put here for the inner region? I would put, well, x, y equals x, and then the upper one would be y equals 2x. Yeah. But then when I come over here, I'm not going to go from x to 2x. I'm going to go from x to what? What's the upper function here? This would be 2 over x. Does that make sense to people? How about the blue? You guys know what these limits of integration would be for the outer integral? 1 to rad 2. There you go. Now this is doable. So decision to make. Should I work it out or let you guys work it out? I guess I'll tell you that if you work it out, you're going to get, I think what you get is you get 2 times the natural log of the square root of 2, which can also be written as the natural log of 2. So it's a really nice answer. And that's using log laws. So again, we could decide how much to do with that. I have another example.
So if we see a notation that just has, like one of the homework questions, has a double integral and just says dy dx, so we assume they're asking us to integrate 1. If they don't put a 1 in there.
Yeah, I guess if the book doesn't write 1, yeah, we're integrating 1. That was even in Calc 1, right? If it just said integrate dy, you're integrating 1, right, with respect to y. But what's kind of cool here is that it actually has a meaning now, right? So the computation will show that the area of this region is the natural log of 2. That's a nice problem. So here's another problem. Let's how about this? Let's find the volume above the unit circle and below the plane z equals x plus 1. Does that make sense? I have to think about that. I mean, let me draw 3 space for a minute. Here's x, here's y, here's z. My unit circle, so my region R, I'm telling you is this, right? The unit circle right there in the xy plane. Now what does this plane look like? Z equals x plus 1. This is what the book called a cylinder, right? Because we don't care what y equals, right? So maybe what I should do to think about this is I should just look here in the zx plane. Of course, we're kind of looking at things backwards. I mean, you almost have to imagine you're on the other side of this square window I drew, so that this is positive and this is positive. So here, let me draw. Here's my Calc 3 student back here, looking and drawing z equals x plus 1. So he sees that it has a z-intercept of 1, so that's up here, and a slope of 1, so he's drawing a line in the window like that. If this makes sense to you, that's amazing. And then you know, actually, right there, I guess it would have to hit. What point is that? That's the point. -1 for x, 0 for y, and then z would be 0, right? But you get this kind of, yeah, so this plane that I'm talking about, if I kind of drew it again, you have your unit circle, and then there's this plane going up through that point and kind of covering everything. And so the shape of the solid, I guess it would look kind of like this. It would kind of, from a side view, it would look kind of like this, right? Does that make any sense to you? Okay. Well, how do I do it? I know how to do it. I need to do the double integral over R, where R is the unit circle. of what? What's the function? Well, the function of this plane, right? If that's my surface, it's just x plus 1, right? That's the equation. Z, it's whatever z equals, or f of x, y. But here, y isn't even involved, so it's...
But we're not subtracting off the unit circle, we're just doing x plus one.
We'd be subtracting zero.
Yeah, because there's no volume underneath. Because this, we're saying, when I say above the unit circle, I mean in the xy plane, right? Yep, Aaron?
Slope of that plane is 1, right?
Yeah, I mean, viewing in the window, when Calc 3 student draws it, yeah, that's how he did it. He did a slope of 1.
You could just do this in geometric. But you
Oh,
could-
sure.
Yeah, I mean, it's just.
So we could check our answer.
Yeah.
That's nice. Yeah, so maybe we'll get a nice answer. Let's see. But again, what I'm interested in here is Calc 3. So let's see if we can do the Calc 3. Do I want to do dx dy or dy dx? Doesn't matter. Why don't we do dx dy just for fun? Dx dy. Let's put my x plus 1 here. All right, so what are the y values? The y values, again, so let me draw the unit circle again, right? And so the y values we want are what? Y equals -1 to y equals 1. That's okay? Hey, Paul, you didn't use any symmetry here. Why not? I mean, look at the shape, right? Do you see how it's higher in some places and lower in some places? It was hard for me to see, although I almost feel like after I solved the problem, I could go back and figure out a way to get the symmetry involved. But if that's the case, then why do it, right? So I'm just being safe here. I don't have the kind of symmetry I had before with the surface. Okay, so now we're integrating dx first, so we really want to think about the unit circle as two functions. I'll call them the pink function on the right here and the brown function on the left here. So what are those functions? Again, we have to write it, we have to solve for x, right? I mean, to get the pink function, I know that x squared plus y squared equals 1. So x is going to be the square root of what? 1 minus y squared. Yeah? So this is the square root of 1 minus y squared. And the lower limit would be x equals negative the square root of 1 minus y squared, right? Because when you solve for x, you're supposed to put a plus or minus, and that gives you these two curves. So in theory, all I have to do is I have to do that, and I can then get the volume. All right, request was made before we solve the rest of this. We're going to go back and try and get natural log of 2. Let's see if we could do it. Well, luckily I'm integrating 1. That's usually pretty easy. So let's see. The first integral here, we get the integral from 0 to 1, and that's dx. But on the inside, when I integrate 1, I get y. And that's from y equals x to y equals 2x, right? And of course, when you substitute in then, what do? 2x minus x, which is x. So I'm almost there, I think, for the first piece. Now, let's see if the second piece might not work out so nice, right? Well, it's the same idea, right? So you're going to integrate from 0 to 1. What goes in here if I kind of skip a step, right? Because again, it's going to be y.
The second part, yeah.
What's that?
Don't you mean 1 is square root?
Oh, yeah. Thank you. This is a 1, and this is a square root of 2. Thank you. 1 to square root of 2. And what goes in here? We're going from x to 2 over x, right? So that won't come out quite as nicely. Maybe I'll write it as, I'll write it as 2 over x minus x, and I'll just leave it that way. Okay, dx. So, let's see what happens. Maybe I'll just work them out kind of a piece at a time. So this one here, I get 1/2 x squared, evaluated from 0 to 1. So that's 1/2. And the other piece here, so plus, this piece here, when I integrate it, the first part gives me, if I factor the 2 out, I'm integrating 1 over x, right? So I get 2 times the natural log of x, right? Minus 1/2 x squared. And that's going from 1 to the square root of 2. Bless you. So here I kind of have more to write. So let me write it out. I have 2 times the natural log of the square root of 2 minus 1/2 of the square root of 2 squared. Then I have to subtract what I get when I plug in a 1. What's the natural log of 1? 0. I need to subtract what I get when I plug in a 1 here, so it becomes plus 1/2 times 1. Wow, okay. So why does it all work out? Well, because here I have a half, here I have a half, that's 1, but here I'm subtracting 2 over 2, which is also 1, so all the pink goes away, and then I get basically 2 natural log of 2 to the 1/2 power, which if I bring the 2 up and kill the 1/2 gives me the natural log of 2. So there's the finish of that. Should we finish the other one? I think so, huh? So we had been here. I want to find the volume of this solid. So we wrote it this way. We're going to integrate dx to start. You know, one nice thing, I guess, about integrating dx to start here is that we're going to get some x squareds. And that's actually good because of the limits we have. So let's see what happens here. I get, this is the integral from -1 to 1 dy. And what I'm left with inside, so let's see, this is 1/2 x squared plus x, evaluated from where to where? Well, again, from x equals negative square root of 1 minus y squared, and x equals positive square root of 1 minus y squared. So here's where, again, symmetry really helps here. You guys, think about this term, right? I'm going to have 1/2 stuff squared. And then over here I'm going to be subtracting 1/2 other stuff squared, but aren't these the same? Do you see that? Because look what you're plugging in. So I guess the only thing to worry about now is what I have, I guess, would be x. So we get the square root of 1 minus y squared, and then we have minus the negative, so plus the square root of 1 minus y squared. Yeah? Okay, so what's this equal? this equals 2 times the integral from -1 to 1, the square root of 1 minus y squared dy. Okay, choices to make. I could do it geometrically. I could do it with an inverse trig sub. I guess we could do it in polar, but that's next time. Preference? You want to see a trig sub? Geometrically? Geometrically, I guess what I'm thinking is, this is I'm integrating the function x equals the square root of 1 minus y squared. What is that? That's x squared equals 1 minus y squared. So that's the unit circle. I'm really integrating part of the unit circle, this part, because it's positive x, from -1 to 1. So what's the area of the unit circle? It's pi r squared, right? So this is half of pi times 1 squared. So I claim that this is pi over 2. So I claim that what we get is 2 times, and then we just worked out that that should be pi over 2 if I did everything right. And so I'm getting that the volume actually is pi. Kind of nice. The volume of that green thing is pi. Could I compute that another way with an inverse trig? Maybe.
Yeah.
Let's show what I would do here. So say I want to use an inverse trig sub. So my hunch would be, okay, which kind of inverse trig sub do I need? This is another inverse sine one. So again, I guess what I'm saying is there are 3 inverse trig subs that you sometimes make. If you have a squared minus u squared, you might try theta is the inverse sine of u over a. If you have a squared plus u squared, you might try theta is the inverse tangent of u over a. And if you have u squared minus a squared, you might try theta is the inverse secant of u over a. So these are my little things in the memory box from Calc 2. That's why I said this is an inverse sine one. I mean, it's an inverse sine of what? Of y, right? So that's kind of nice. So then right away what I like to do is I like to say that the sine of theta is y. Then you can compute dy. dy is what? Well, if y is the sine of theta, what's dy? Cosine theta d theta. Right? And so now we're kind of like set up to make that substitution. So let's do it. Let's do it in green here. So here's where I was, right? I'll come down here and I'll say that this is equal to 2 times the integral. Well, okay, it's the square root of 1 minus sine squared of theta times cosine of theta d theta, right? Maybe I'll leave these as y values. I think that's probably the thing to do for now. You don't have to. I mean, because we know what the inverse sine of 1 and the inverse sine of -1 are. Change them or keep them? That's kind of personal preference. Keep them? Okay, I'll keep them. What's the square root of 1 minus sine squared theta? What's 1 minus sine squared? Cosine squared. Right? If I take the square root of cosine squared, I get cosine. So this is a cosine of theta, right? All this parentheses. And so what I'm really integrating is 2 integral, again, y equals -1 to y equals 1, cosine squared theta d theta. Well, I need a little help on that one from a trig identity. I think this Calc 2 just had their test on this stuff. Cosine squared is the same as 1 plus the cosine of 2 theta all over 2. Oh yeah, the 2's cancel. So we get theta plus, now when you integrate the cosine of 2 theta, you get the sine of 2 theta, but because of the chain rule and, or your u substitution, you have to put a 1/2 out front, right? And I want to plug in, but I'm still have y's because you guys didn't want me to switch them. So I can't yet. I have to start to do a little more here. And so where it used to say theta, I can write what? Inverse sine of y plus, and here's where another identity comes into play. The sine of 2 theta is the same as 2 sine theta cosine theta. So the 2's cancel with the 1/2, and you get this sine theta cosine theta. And now you have, what we should have done a while ago, maybe. Back here when you have sine of theta is y, how do you write that as a fraction? Y over 1. So my picture on the right triangle with theta in it is that sine is opposite over hypotenuse. So this is y, and that's 1. So what's this? The square root of. Hey, and if you get that, and that was in your integrand, that's a good sign that you're doing something right. I was telling my Calc 2 people that. So we like to draw that picture. But anyways, back to my program. Where it says sine of theta, I can write y. And where it says cosine of theta, I guess what I could write from the picture is the square root of 1 minus y squared. And we're evaluating this mess from -1 to 1. Now, whether I plug in -1 or 1 into the second term, that's going to give me a 0. When I plug in 1 or -1 to the first term, what's the arcsine of 1? Isn't it pi over 2? So what's pi over 2 minus negative pi over 2? That's pi. Yeah, I think that might have been worth for you to see, just as a refresher. But we are out of time, and we are on break.